So this one we are just kind of completed naming, and I did give you a worksheet on this. Okay, so try and complete that one. So I'll just do a few more questions about this, TK, about naming compounds with multiple functional groups and with side chains. So let's try and do a few more. Just this is one carbon with CH3. So I've got 2 carbons over here, 3 hydrogens, 2 hydrogens, and I've got an OH here. And this one is an aldehyde. And what else? Let's have a Cl here as well. So this is H. This one will have H. So I'm just going to do just one more. The first thing when you're naming compounds, the very first thing is you find the longest chain with the maximum substituent groups, and that's going to be this one. It's 5, and that's your main chain. 5 is pent. The longest one was this one, but remember I have to include the maximum groups should be attached on the longest chain. So we took this one, and it's going to be, it's unsaturated. So there's going to be, instead of AN, it's going to be EN. And plus it's got multiple functional groups. It's got alcohol, it's got an aldehyde as well. And remember we talked about aldehydes having or being more important. Okay, so aldehydes were more important. I mean, this is the preference list. So aldehydes were more important than alcohols. So if aldehydes are more important than alcohols, so what you're going to do is you're going to call it an aldehyde. You're going to call it an aldehyde. An aldehyde would be given the shorter number, the smaller number. That's going to be 1. Then this would be 2, this would be 3, this would be 4, and this would be 5. So that means the aldehyde is at 1. You don't have to write that, but even if you write it, it's not going to be incorrect. The double bond is at position number 2. So in front of EN, that's where you write down the double bond. Everything else is going to be a branch. So this is a branch, this one is a branch. So you've got 1 carbon atom branch, that's methyl. You've got a 2 carbon atom branch, that's ethyl. The OH is now considered a branch, that's hydroxy. And you've got these 2 chlorine branches, which would be referred to as chloro. So you've got a list of branches which would be written alphabetically, and this one, the first one would be chloro. Alphabetically, then I think it's ethyl. Then you've got hydroxy. And after that, it's going to be methyl. So these are all your branches. So, Momna, can you hear me?
Yes, sir.
Achha, theek hai. So we just started with naming. I'll share the previous lectures with you as well. So we're just going to move towards isomers after this.
Sir,
yes.
I'm sorry I joined late. Did I miss anything?
No, we're just recapping naming, and then we're going to start with the next topic. Okay? I mean, next organic thing. So anyways, that's your main chain. Longest chain, 5 carbon atoms, aldehyde, that's more important. So it's going to be an al at the end. Double bond, so instead of AN, it's EN. And you've got all these branches. Ethyl, 2 carbon atoms. Methyl, that's 1 carbon atom. You've got hydroxy, you've got 2 chloro. So that's this over here should be dichloro. And then you just start writing the positions. So the methyl one is at position number 3. So this one is 3. Methyl, the hydroxy is at position number 5. And the 2 chloros are at 5 and 5. Both of them are at 5. So it's going to be 5, 5 dichloro. And the ethyl group is at position number 4. So that's the way you're going to name it. Okay, so that's, I mean, most of the questions would be almost pretty much less complicated than this one. Not as complicated. I mean, you'll get something similar to this one. So the point is, just remember when you've got multiple groups, you name the molecule based on the most highest precedence group, and you also give it the smaller number. You're going to count from the side that gives the smaller number to the highest precedence group, which in this case was carboxylic acid. So you're going to call this the 1. This would be 2. This would be 3. And the naming was done in 3 parts. You had the main chain, you've got branches, and you've got the position of those branches. Now, we're going to move towards isomers now, and we're going to start talking about isomers. And we will start initially with, I mean, first thing, what is isomers? So isomers are, and we're talking about structural isomers at the moment. So structural isomers. The definition is that they have the molecules having the same molecular formula. So they have the same molecular formula, which means the same number of atoms. You've already done this one in your O levels, but they have different. They've got different structural formulas. So that's what an isomer is. Now remember, I'll also give you some importance of why do you even study isomers in the first place? But why do we care that they have the same molecular formula but have different structural formulas? So the thing is that isomers are really important when it comes to analytical chemistry, because the very first thing that you know about an atom is this thing. I mean, that's the very first thing. Like if I'm given a molecule or a substance and I'm being told to analyze that substance, the very first thing I'm going to figure out is the molecular formula. That will not tell me, I'll get an idea of how many oxygens it has. I'll get an idea of how many carbons it has. I'll get an idea of how many hydrogens it has, but I'll have no idea how the atoms are arranged. So which is why when you're doing analytical chemistry, the first thing, if you're studying a virus or a bacteria or any chemical, any organic molecule like an enzyme, the very first thing is you get the molecular formula. That's the first thing. And then you start analyzing it. Then you start thinking about it. Maybe the 3 carbon atoms are arranged in this manner, right? So that's a possibility. So maybe the 3 carbons and the 6 hydrogens and the 2 oxygens are arranged in this manner. That would make it a carboxylic acid. So I'm going to guess the properties of the compound based on the structures that I come up with. And whatever the molecule matches, the properties match with whatever molecule I draw, then I'll get a pretty good idea of what that molecule is. So that's one. I'll do some more guesswork maybe. The 3 carbon atoms are not arranged. The double bond is somewhere else, and the OH is somewhere else. So maybe it's a ketone plus an alcohol. So that's also C3H6O2. Maybe it's something like this. It might be an aldehyde with an OH group at the other side. And then this too could have other versions as well, like it could be double bond O and H, and the OH group is over here. So maybe it's this one, or and I can keep on coming up with different structures with the same thing. Okay? Because remember, when you're doing analytical chemistry, the first thing that you have to analyze is what could be the identity of this molecule? I mean, you get this information, but you don't know what the structure of the molecule is. Because remember, we draw structures all the time, but remember, making the structure or figuring out the structure is not an easy thing. Because most molecules, I mean, all molecules are kind of invisible. You can't see them. You can't see the oxygen. Like, I mean, the only thing you could do is you can guess them by figuring out their chemical and physical properties. So what else can you draw? Like you've got C3H6O2. So you can come up with more things. You could have the double bond O. It could be an ester. This one will have 3 hydrogens, and the one on the other end will also have 3 hydrogens. So that's another possibility. Or it could be that you could have another ester where, yes, Abdullah, this is isomerism. So you could have another ester, which could be this one. Or maybe apart from that, I can't have any other esters. So that's another one. So all these are isomers. And remember, isomers are really important because that is the first step in figuring out what the structure of this molecule is. Well, once I've drawn sufficient isomers, the next step is I'm going to figure out the properties of each one. Like what I can do is I can check the pH of the solution. If the pH is acidic, that means it's this molecule over here. Okay, so most of the structures that you study, they're the kind of guesswork. Okay, and isomers help you in guessing the structure of whatever this is. But remember, I can keep on going. I mean, I can draw more and more isomers of this C3H6O2. So maybe there's a double bond. Okay, it could be an alkene as well. And there's an OH, and there's another OH, and there are 3 hydrogens, and this is 1 hydrogen over here. So that's also C3H6 and O2. Okay, and we can keep on going. It's I mean, even this version could have many isomers, like the 2 OH groups, they might be at different places. So there are endless, I mean, a lot of times there are endless possibilities of isomers that are possible. And we can just keep on going. The C3H6O can have many isomers. I think at least, I mean, I would be able to draw around 4 or 5 more isomers if I just keep on going like this. So it's just 3 carbons, 6 hydrogens, and 2 oxygens. And every time we can just come up with more and more structures which have the same exact molecular formula, and that's your structural isomers. So is this point clear? I think you've already done this. Is this clear? Yes or no?
Yes.
Okay.
Yes.
I said now the bigger question is when you're being asked to draw the structural formulas. Remember, a lot of, especially your paper 2s, there were a lot of questions on structural formulas. I mean, a lot of organic questions are kind of structured in this way, that they tell you that there's a molecule, they tell you that it has a double bond. I mean, they'll give you some information about it, and they'll ask you to draw the isomers. Like, okay, it's got a double bond, so it might be one of these 2. I mean, I can come up with more ones, like just keep on switching the position of the OH groups and you can make more isomers. So a lot of organic questions start out this way. So the important thing when you're talking about structural formulas is you need to realize what is not a structural isomer. I mean, that's very important. Now this thing is, I mean, drawing the structural isomer is one thing. Making sure you know what is not a structural isomer, that's even more important, and that is rotated, twisted, flipped around versions are not structural isomers. A necessary condition for isomerism, structural isomers, is that the connectivity has to be different. Okay? Isomers must have different connections. I mean, the bonds need to be connected in some different way. So must have different connections. Because remember, this is not the actual shape of the molecule. This is just a two-dimensional, because in reality, carbon is tetrahedral. This carbon is tetrahedral. This carbon is fan-shaped. So this is not the actual shape of the molecule. So if I draw one molecule and it's got an OH and it's got an H and an H and a, let's say, a Cl over here and an OH. Just 1 second. Another OH and let's say fluorine over here. And I draw another molecule, which kind of looks different. And this other molecule is just a twisted, flipped around version of the same thing. So there's an OH, and there's an H, and there's another H. And over here, so over here, I've got an OH, and I've got a Cl, and I've got an F. Now, this molecule kind of looks different. But if you just look carefully, they're exactly the same because the connections are exactly the same. Like you got a carbon atom, which is bonded to 2 hydrogens and 1 OH. You've got a carbon atom over here as well, which is exactly the same. It's bonded to 2 hydrogens and 1 OH. I mean, the direction of the bonds really don't matter. I mean, as long as this H is bonded to the same carbon atom, it's kind of the same thing, because remember, this is not the 3-dimensional representation of the molecule. Whenever you draw structural formulas, you only show connections, which atom is connected to which atom. It doesn't actually show you that the bond is pointing upwards, or is it pointing downwards, or is it on the right side, or so the directions are just arbitrary. So just remember that this carbon atom is identical. What about the second carbon atom? If you look at the second carbon atom, this carbon atom is bonded to Cl, to an OH, and to an F. This carbon atom is also exactly the same. It's bonded to a Cl, an F, and an OH. This one is also bonded to a Cl, an OH, and an F. So is this point clear? Yes or no? Is this clear?
Yes, sir.
So this Anna, is this clear?
Yes.
So just remember what is not an isomer. A lot of times molecules would kind of look like isomers, but they're not actually isomers. So I'll just give you a quick question. Here's 4 carbon atom. It's got an OH, H, and I'm going to try and draw isomers of this. So can you hear me properly?
Yes, sir.
Yes, sir.
Okay, so then I think it's just the website that's hanging up. So here's a molecule. I'm going to draw a couple of isomers for this. So and this will be so that's one. Let's do another one. I've got this molecule. And I've got let's let me just quickly trying to draw all these isomers. Just 1 second. And I've got one more, let's say. So now I've drawn these molecules. Can you pinpoint which two molecules are exactly the same? I mean, which ones are isomers and which two molecules are exactly the same? I mean, let me give them numbers as well. This is A, this is B, this one is C. You've got D and you've got E. So which of the two molecules do you think are exactly the same?
B and D.
B and
D.
I said these two. I said, look at the connections. Are the connections exactly the same or not? Okay, so I'm going to start off with the middle carbon atom. Okay, you got a carbon atom in the middle. You've got a carbon atom in the middle over here as well, right? I said, so this carbon atom is bonded to 3 carbon atoms. This one is also bonded to 3 carbon atoms, right? So that's kind of similar. But the middle carbon atom is bonded to an OH. This middle carbon atom is not bonded to an OH. So that means that
A and D.
Okay, A and
D.
so ठीक है वो भी देख लेते हैं. As the first one is the first one clear? B and D they're obviously different. Okay, because the connections are different. I said then let's start with A and D now. A and D, the 4 carbon atoms are connected in a line. They're all one after the other one. This one is a branch structure, so it's kind of different. It's 3 carbon atoms in a line, and in the middle one there's a branch. So the connections are different. So these two are different. So tell me the ones which are exactly the same. The A and D are the same. Is this clear? A and D are different. A and D are different. Exactly. So which one? Remember, don't focus on the shape. Don't focus on the direction of the bonds. Okay. Focus on the connections. Are the connections the same or not? So if I
B and E.
Okay, B and E are exactly the same. Okay, if you look at B and E, they might look different. I mean, shape-wise, they might look different, but the connections are exactly the same. Because you've got a middle carbon atom with an OH. Over here, you've got a middle carbon atom which is with an OH. Okay, you've got an OH here. And that middle carbon atom has a CH3, CH3, and a CH3 on 3 sides. This middle carbon atom over here has a CH3, CH3, and a CH3 on its sides. So that means this molecule is bonded in exactly the same way as this molecule. Is this clear?
Yes.
So just wait 1 minute, okay, for the azan. Just 1 minute. So let's continue. Okay, so I just wanted to talk about A and C. Look at A and C. Okay, they are also exactly the same. You've got a carbon atom with 2 hydrogens. Okay, focus on this carbon atom. You've got a carbon atom with 2 hydrogens and an OH. And after that, this carbon atom is connected to a carbon with 2 H's. This carbon atom is connected to carbon with 2 H's. Then it's again connected to a carbon with 2 H's. I mean, this part is the same. Then that one is again connected to a carbon with 2 H's. This one is also connected to a carbon with 2 H's. And at the end, there's a CH3. This one is also a CH3. So these two are exactly the same. They're just twisted versions of the same thing. Is this clear?
Yeah.
Okay. So remember, keep an eye open for this, because a lot of times people make a mistake that they're drawing the same molecule over and over again, and they think that they're isomers when they're not actually isomers. Okay. So remember, for isomerism, structural isomers to form, the connections, they have to be different. They have to be connected in some different way. Okay. So hopefully that's clear. And we can talk about the types of structural isomers now. Okay, the next thing that we're going to talk about is the types of structural isomers. You can classify them, and in your organic exam, they'll be very specific. A lot of times they will be specific. A lot of times they'll just ask a general question, just draw isomers. But sometimes they would be very specific. Types of structural isomers. So, and remember, not all isomers can be classified as types. I mean, you have structural isomers, but you can't, like look at the ones over here. You can classify some of them, but not all of them. Okay, so this classification system doesn't really work all the time. Now, the types of structural isomers, the first one, option A, those are called your branch or chain isomers. So branch or chain isomers. Now, in this, all you have to do is change the structure of the carbon chain, or change the connections or connectivity of the carbon chain. Connect all the carbons in a different way. So I've got 4 carbon atoms in a row. Let's say 5 carbon atoms. What I can do, so I'm just going to focus, I'm forget all the other things. I'm just going to focus on the carbon chain. So what I can have 4 carbon atoms in a row, and there could be a carbon that would be coming out of it, or I can have 3 carbon atoms in a row, and there could be 2 carbon atoms that would be coming out of it. So remember that, and that's probably it. I mean, I can't really rearrange the carbon chain that much. That's pretty much it. So I can have 4 carbon atoms in a row, and I could have a branch that's coming out of it. Can't really do much over here, because if I put the branch on the other one, that would kind of be the same thing. I mean, that would be exactly the same connectivity. It's just a flipped, I mean, pick this up and put it the other way around, you get this. So it's kind of the same molecule. It's not a different molecule, okay? So is this clear? The first one, option A, is this clear?
Yeah.
Okay, so that's number 1. Then the second one, you just change the carbon branch, okay, which we did over here. You had branch isomers, like these two were branch isomers. I had 4 carbon atoms in a row. Now I had 3 carbon atoms in a row, and there was 1 sticking out of it as a branch. This one was also a branch isomer. I changed the carbon branch. The next one, option B, the second option, that's a positional isomer. So what you can do over here is just change the position of a certain group or a group of atoms. So just change the position of a group or an atom or anything or a structure. So for example, I had an alcohol with 4 carbon atoms. Okay. Now what I'm going to do is I'm going to ignore all the other stuff. So I've got an OH on this carbon atom. What I can do is I can have another molecule, and I can have the OH on the second one. So these two are isomers. These two are positional isomers, because the only thing I changed was the position of the group. Same thing over here. Like if I have a double bond, and what I can do is I can put the double bond somewhere else. Okay, I mean, that's probably the only 2 positional isomers that are possible in this case. So is this clear? Positional isomers?
Yes, sir, but aren't they the same thing as structural isomers?
These are types of structural isomers. I mean, they're exactly the same thing.
Okay.
Okay, I mean, they are uski types and okay, they're types of structural isomers. So they can be very specific. They can ask you to draw a very specific type of structural isomers. They might call you, for example, they give you this molecule and they tell you to draw a branch isomer. So when you, or a chain isomer, so what you have to do is you have to draw one of these. Or they might tell you to draw a positional isomer. When they ask you to draw a very specific isomer, then just change the position if they're asking for the positional isomer. And the last one is a functional group isomer. Now, what happens in this one is that you completely change the functional group. I mean, it's still an isomer, but with the functional group completely changed. Okay, we did have a lot of functional group isomers. For example, I can draw other ones, like I had propanoic acid. Okay, this was the first one that we did. So I had propanoic acid, double bond ONOH, and the rest were hydrogen atoms. Okay, just assume that they are hydrogen atoms. Now that's a particular functional group. And what I can do is I can change it completely. I can turn it into an alcohol and turn it into an aldehyde. Okay, the rest are all hydrogen atoms. So I had a carboxylic acid, and now I've drawn an isomer which is not a carboxylic acid. It has the same number of atoms, so it is an isomer, but it's not a carboxylic acid. It's an aldehyde plus an alcohol. And I can draw other ones as well. Like I can turn it into a ketone as well, and an alcohol. These are your 6 hydrogens. So this one over here is a ketone plus an alcohol. Or I can turn it, the most popular ones are esters. Carboxylic acids have isomers which are esters. So I can turn it into an ester functional group as well. So the point is, there's no limitation to how you make an isomer. But when they specifically call for a functional group isomer, you have to make another molecule that has the same number of atoms, but it doesn't have the functional group that was present in the first one. So is this also clear? Yes or no? Is this clear? Anna, Momna, clear? Mariam, is this clear?
Yes, sir.
Hania?
Yes, sir.
Yes, sir.
Achha, so remember the types of isomers that they're looking for specifically. And then, so you got these 3 types. We're going to do past paper questions on this, TK. Then we'll go into a lot more detail. We'll practice a lot. Moving on. You've got other types of isomers as well. And these are, so structural isomers is done. TK, so remember this. We're done with structural isomers. We'll do past paper questions at the end. We're going to move towards the other types of isomers, which are stereoisomers. Now, what are stereoisomers? Stereoisomers is I mean, the first example that comes to mind are your two hands. I mean, your two hands, they look exactly the same, but there's something different about them. I mean, they're exactly the same. Everything about your right hand is the same as your left hand, except for one thing, and that is the orientation of the fingers and the orientation of everything. They're basically mirrored versions of each other. So the same thing happens with molecules as well. Sometimes you'll have two molecules that would look kind of exactly the same, except that the orientation of the bonds would be different. For example, if there's a glove with right hand mentioned on it, only your right hand would fit into it. Your left hand will not be able to fit into it because the the fingers in your left hand or the orientation of the fingers of your left hand are different from the orientation of your right hand fingers. So those are stereoisomers. Stereoisomers have that they have the same molecular formula. So they're molecules having the exact same molecular formula and they also have the same structural formula. So even the structure is same, identical. Exactly same connections. I mean, you can't, just like your two hands, the connections are exactly the same connections. The only difference would be different orientation of the bonds in space.
So we're just flipping it.
We will study this. So you've got different orientation of bonds in space. So we're gonna discuss one by one. This is stereoisomers. But remember about stereoisomers that the structural formula would be exactly the same. The molecules would look kind of exactly the same connections, everything is the same. But the bonds or the three-dimensional formula would be different. Or you can say that the three-dimensional spatial arrangement or the three-dimensional shape would be different. So we're going to start with the first one, and the first one is known as optical isomers. Let's start with optical isomers first. Also known as enantiomers. I mean, that's another name given to them. And there's another term that's sometimes used, and we can just write it over here. There's another term known as a racemate mixture. Racemate mixture. So that's a mixture of two enantiomers. So it's a mixture of two optical isomers. So that's the first one, option number one. And I'll just write the conditions at the moment. The conditions are, number one, a chiral center must be present. So you're basically looking for a carbon atom making 4 single bonds with 4 different groups. That's what a chiral center is. So you're looking for a carbon atom that makes 4 single bonds. It's going to be tetrahedral. And it's going to be sp3 hybridized. So you're kind of looking for this thing. You're looking for a carbon atom And remember now the geometry of the molecule is very important. The shape of the molecule is very important. So we're going to draw the three-dimensional representation of these things. So you've got a tetrahedral structure, and all four groups must be different. So you've got an OH over here, you've got a CH3 over here, you've got another carbon chain CH2, and let's say you've got a Cl over here. So the point is that you're looking for a carbon atom which is making single bonds, and all four groups that it's bonded to are different. This is what a carbon atom looks like when it's tetrahedral, when it's making three bonds. So this is how, where is it? So I mean, this is how it looks like. We're looking for this carbon atom that is tetrahedral, making four bonds. If you remember geometry of the molecule, carbon atom makes four bonds, it's tetrahedral, angles are 109.5, and all four things that it's attached to, they must be different. That's the first necessary condition, and that's probably the only necessary condition for this to happen. So I'll explain optical isomers later in the next class. The only thing we've done so far is we've just discussed the necessary conditions for an optical isomer to form. That the molecule must have a chiral center. It must have a carbon atom, which is making four single bonds with four different groups. If you don't have such a carbon atom, and if there is no chiral center present, that means optical isomers are not possible. So yeah, is this all clear?
Yes,
Yes.
sir.
Sure, let's continue tomorrow then.
Okay, Allah Hafiz.
Okay, take care. Allah Hafiz.
Love you.